Today we are talking about half-life and double time. You can even go to say triple time, half-life, is the amount of time that it required for a quantity to reduce its initial value by half. And then so that's why the half is here. And then double time is the amount of time it takes it to double. This is an exponent. So if we were to say how long it would take to triple, it would be 3 to that same exponent. So this is kind of, they're all very similar formulas, so we're kind of grouping them all together. So when we're doing this, what does the exponent mean? Time over double time or time over half time? What does it mean? Well, the top is how much time you're allowing. Time allowed. So whatever it is, over an hour, 800 years, whatever. And this number down here is the actual half-life, or how long it takes the quantity to have, or how long it takes it to double, depending on what it's, what the material is. So half-life or double life. Okay, so that if you divide those, it figures out how many half-lives you've had or how many double lives you've had. Okay? So what this says here. If the half-life of a substance is 2 days, how many half-lives does it go through in a week? So in 2 weeks. So this is the idea. So we're talking about, this is the exponent of this problem. So we're taking this piece or this piece right here and determining this information. Now, a lot of us, we could just go through it mentally. Like, if the half-life is 2 days, then it's 2 days, then it's 4 days, then it's 6 days, then it's 8 days, and then we just go up to 14 days for 2 weeks. Perfectly fine. Okay? But let's say we had 11 days. Or the half-life was 15 weeks, and we wanted to know how long it would be in 2 weeks. So when it's not a perfect half-life, the time allowed is not perfect, we can just do it this way. So if the half-life of the substance is 2 days, so remember half-life goes on the bottom, and the amount of time we're allowed is 2 weeks. Now, these two both have to be in the same units. So it would be 14 days over 2 weeks, so it's 7 half-lives went through. So that's an example of how that exponent can be changed and why it is what it is. So 7 half-lives, that's what we're raising it to, how many half-lives we have. Same idea with doubling. How long does it take to double? If you have 3 grams of a substance, how many double lives does it go through in 20 minutes or in 1 hour? And in 1 hour. So it's the same idea. A half-life or double life always goes on the bottom, and how many touch time we're allowed goes on top. So this is 10 minutes. Nice. So this is 10 double lives. 10 lives. I don't know. It doubled 10 times. And then say in an hour. So remember, it does still have to be the same units. So 1 hour is 60 minutes. And over 2, so this goes through 30 double lives, or it doubles 30 times. Okay, so then we have just an example of a problem. I talked already about what the half or the 2 was for. That is the base. That's the base. So for example, the rate of change for half-life is -0.5, or it's -50%. So when we do this, if we put this into a regular formula, this number right here, this number is half-lives you went through. And this number right here is 1 minus the half, or 1 minus 0.5, which gives us that half in the base. So same thing for double. The difference is the rate is 100%. So it's 1 plus 1 down here, and T is the number of times it doubles. And that 1 plus 1 is 2. You know, take with that what you must. So the half-life of carbon-14 is known to be 5,720 years. Dr. Frankenstein has 300 grams of carbon-14 in his experimental laboratory. If untouched, how much of the 300 grams will remain after 1,200 years? Okay, so you have to set up the problem. So 300 grams is the starting value. So this is the formula. Then it's half-life, so that's a half. The top number is how much time we're allowed, so after 1,200 years, and the bottom number is the half-life. Okay, so then you just figure it out. They want, well, I guess in this case, this one, it would be A of 1,200. We should have put 1,200 in there because I didn't just write the formula, I put the 1,200 in. So then if we do the math, it's 259.39888873. So if I didn't ask what to round to, you just got to write the whole thing. And that's just poor writing on my part, that's all. Okay, this one, if untouched to the nearest 100 years, how much will it take to reduce the carbon to 10 grams? Okay, so this would be considered the end value. So remember the way that we set up the formula. The end value goes on this side. The start value goes next to the base. And then we put our half-life, time over half-life. That's our formula there. So the ending thing, when will we have 10 grams? That goes here. The start was 300 grams. We do half-life. We have time. We don't know what the time is, so it's 5,720. Is that how many feet in a mile, too? Something like that, right? I don't know. I don't care. So then we solve this guy like we normally would. This is an exponent. Remember, whenever you're solving for an exponent, you must use logs. There is no other way that we allow. Okay, so divide by 300, and you get your 1 over 30. Or you can figure out the decimal, I just don't feel like it. So 1 half, T to the 5720. And then so it's log base a half of 1 over 30 equals T over 5,720. Doing the log switch. And then we just take this number, whatever we get here, and multiply it by 5,720, a little cross multiplying here. So 5,720 times, I guess this is like 4.9068. We get 28,067.41421. And then they set up here to the nearest 100 years. So to the nearest 100 years, that's that one right here. 28,100 years. All right. Have a beloved day. Have a good day. Bye.